Hi, this is our third video on probabilities covering sections 5.4 through 5.6. So what we're going to start talking about with this video is what's called conditional probability. Now, conditional probability is when we're trying to calculate the probability of dependent events. And the main idea with this conditional probability is that if I have some information, is it going to actually change the probability I'm looking at? So, for example, if I wanted to know what's the probability that someone has a cold, well, if I know that you have a sore throat, then I know you're much more likely to have a cold. So knowing that information actually changes my probability. If I know that you have a sore throat, I know that you're going to be more likely to have a cold. So the notation we use for this is that if we have events E and F, then we say that the probability of F given E, well, we notate that like this, using a vertical line basically in place of the word given. And so again, given is going to be our information that we already know. And then, well, what's the probability of the other event if we, well, know that given information? So I want to go back. Let's take a look at one of the examples from the last video. What's the probability of having one boy out of 3 kids? So again, we already looked at this one. So we created our sample space. We did our branching tree. We know that the sample size was 8. There's 8 different ways we could have 3 children made up of boys and girls. And I want one boy out of the 3 kids. So my event space could be boy, girl, 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 boy, girl, or girl, girl, boy. So there's 3 possibilities for size 3. So my probability of having one boy out of the 3 kids was 3 out of 8, or 0.375. Now, what if I make this a conditional probability? What's the probability of having 2 girls given your first child was a boy? Now again, what's going to happen with these conditional probabilities and these dependent events is that because I'm now given some information, that given information is actually going to make my sample space smaller. It's going to restrict my sample. So if I know that my first child was a boy, well, I only need to look at the possibilities where the first child was a boy, which means my sample space is actually now cut in half. I'm only going to look at the sample where the first child was a boy, which means my sample size is now 4. Now, when I look at my event, there's only one outcome in that event that fits, the boy, girl, girl, so there's a size of 1. So the probability of having 2 girls given the first child was a boy is going to be 1 out of 4, or 0.25. And that's typically how these conditional probabilities are going to work. Remember, probability is just the size of the event over the size of the sample. And so if we're now talking about a conditional probability, our conditional probability is going to be calculated, well, our new sample is that given event, right? What's the probability that what's happened has occurred? That's my new sample. And then my event is that both events have to happen. And that's the key part here, is that top part now is the probability of E and F. I need them both to have occurred, right? Even though my sample space is that the probability of my given, right? And again, my given event happened. My event is that the given event happened and the new thing that I'm looking at has also happened. So let's look at a quick example using some probabilities. So let's say 70% of people like chocolate ice cream, 35% of people like both chocolate and strawberry ice cream. So what is the probability that someone who likes chocolate ice cream is also going to like strawberry? So if I already know that a person likes chocolate ice cream, that is going to affect the probability of whether or not they like strawberry too. And so again, we want to set this up with our sample and our event. And so our sample is that given. The sample space now is we know that this person already likes chocolate ice cream, which means my sample space is, well, the probability that someone likes chocolate, which is 0.7 or 70%. Again, remember you have to convert all those percentages to decimals here. And my event is going to be that they like both the chocolate and the strawberry, which is the 35% or 0.35. And so the probability, again, we just basically follow that formula, and we're going to divide the event by the sample, and 0.35 divided by 0.7 is 0.5, or half. And again, if we take another look at that, that should kind of make some intuitive sense. Right? If 70% of people like chocolate and 35% like both, well, 35% is, well, half of 70%, which means if I'm restricting myself to just the people that like chocolate ice cream, half of them are going to like both. Now, from here, we can also generate our general multiplication rule. So again, here's our formula for calculating our conditional probabilities. If I multiply both sides by the probability of E, basically trying to get rid of the fractions there, I get this formula, and then typically we just rearrange it, write it backwards, and this becomes our general multiplication rule. The probability of E and F equals the probability of E times the probability of F given E. So remember, this is actually very similar to our first multiplication rule for independent events, where, again, it's multiplication. If you see the word and, you're always doing multiplication. And if those were independent, like they were in the previous section, well then the probability of F given E is just the probability of F. If they're independent, it doesn't matter. There's no change by knowing the information. They're completely separate probabilities. So again, this general multiplication rule works every single time. So what is the probability that the first two cards you draw from a deck are going to both be kings? All right, so this is going to involve some conditional probability, but we're going to set it up kind of similar to how we've done some of those other ones. So the probability of getting two kings, well, what's the probability of the first card's being a king, and the probability the second card is a king, given that the first one had to already be a king. All right, and again, that's kind of the key. Remember, with a deck of cards, as soon as I draw one card, my deck is not the same. And so I absolutely have to use my conditional probabilities here. Now, we can also do this and kind of logic it out as well because, well, what's the probability of the first card being a king? Well, that probability is going to be 4 out of 52, right? There's 4 kings in a deck out of the 52 cards in the deck. So 4 out of 52. But now that second one, the probability that the second card is a king, given that the first one is a king. Well, now that's going to change, right? My probability is going to be slightly different here for that second one because my event size is smaller, right? My deck of cards, I took out one of the kings, which means there's only 3 kings left in the deck now. And my deck size has changed too. You know, there was 52 cards in the deck, but I took one out, which means there's only 51 cards left. So the probability that the second card is a king is different than the probability that the first card was a king. But again, we follow our typical probability rules. We multiply those, and then we get our approximate decimal answer for the probability. Now, if I am dealt 2 cards at random 2,000 times, how many of those times would I expect to get a pair of kings? So we're doing an expected value problem here. And again, remember that expected value is just n, the number of probability experiments, which in this case, I'm doing it 2,000 times. And the pair of kings, well, we're using the probability that we just figured out in that last example, the 0.0045, and I get the number 9. So that means you'd expect to be dealt a pair of kings 9 times. So this is kind of how well, Hold'em poker is played. You're dealt 2 cards. And essentially what this is saying is that if you were dealt 2,000 hands of Hold'em poker, you'd get pocket kings 9 of those 2,000 times. All right, on to example 6. And this is one of the maybe the more trickier and a little bit more complicated problems. And but I think this is a really important example worth discussing. So the U.S. government currently tracks all Twitter users to identify potential terrorism suspects. That part is absolutely true. The government and the intelligence agencies are absolutely 100% scanning every single tweet to, well, flag potential dangerous individuals. Now, let's assume the algorithm they use is 99.9% accurate. All right, that part I have no idea about. I'm just assuming, and I'm going to give them the benefit of the doubt. And 99.9% accurate, I think, is pretty good. There are 330 million active Twitter users. Again, that part is accurate. That's a real fact. There's about 330 million active Twitter users. Now let's assume that there are 10,000 terrorists who are using Twitter to communicate. And again, I'm kind of just making that number up. I really have no idea. But we're going to go with those assumptions. So the first question is, well, what's the probability that a terrorist suspect is correctly identified? Well, again, this is given in the problem. If the algorithm is 99.9% accurate, we should convert that to a decimal if we want to talk about probabilities, and it's 0.999, right? That's the probability. So if they are a terrorist, the probability that they are correctly identified is 0.999. Well, then how many terrorists would we expect the government to catch? Again, this is an expected value problem, n times p. So we know there's 10,000 terrorists times that probability of catching them, which is 0.999, and we get 9,990, which means we would expect the government to actually catch 9,990 terrorists out of the 10,000, which means they would just miss 10. And again, that's pretty good, right? That's a 99.9% accuracy. Even though that's really, really accurate, you're still going to miss things every once in a while. Nothing is perfect. But here comes the other half of this problem. How many people would we expect to be incorrectly identified as terrorists? All right. So again, the algorithm works 99.9% of the time, which means it's going to catch 99.9% of the bad guys. But, well, even if it works 99.9% of the time, we know that that means it's going to not work 0.1% of the time, or 0.001 for a probability. So those times where it does work incorrectly, well, it's going to flag some innocent people as terrorists, even though they're not. Well, how many people is that going to be? Well, first of all, how many people are innocent? Well, if there's 330 million users and 10,000 are terrorists, then, well, we can subtract out the terrorists. And that means that of the people on Twitter, 329,990,000 are innocent. And then our expected value, we multiply that number times the probability, 0.001, and we see that we would expect 329,990 users to be incorrectly identified as terrorists, or flagged and put on a terrorist watch list or a dangerous persons watch list. So this leads us to the actual conditional probability. What is the probability that someone is a terrorist given that they have been identified by the algorithm? Well, we're going to go back to our normal probability rules, the event divided by the sample. All right, and now my sample is just going to be the number of people who are identified, right? That is my given. If you are identified, that is now my sample space. Well, we know that they correctly identified 9,990 terrorists, and they incorrectly identified 329,990 innocent people, which means in total, the algorithm flagged 339,980 individuals, right? The Twitter algorithm that the intelligence agency used flagged that 339,980 people. Well, how many of those were terrorists? Those were the 9,900. And if we divide that, right, the event divided by the sample space, we get 0.02938, which is approximately 2.94%. So that means that of the people flagged by the algorithm, less than 3% of them were actually terrorists and dangerous individuals. So does this mean that we should keep, well, should we keep these government programs to scan Twitter and social media to try to identify these dangerous individuals if it's only working, well, less than 3% of the time? Or wait, is it working 99.9% of the time? Oh, well, it would probably depend on which side of the argument you're on to depend upon, well, which one of those probabilities you use. And this is the beautiful part about America. I can't answer this question for you. I can't answer for you whether or not you think these mass surveillance programs are justified. Obviously, they're effective. They catch most of the dangerous individuals. But out of all the individuals that are flagged and will then go on to, well, higher degrees of, well, delving into their personal lives, well, is that a fair trade-off to basically start spying on American citizens who have done nothing wrong? I don't know. That's not for me to answer. That's for you to answer. And hopefully, this class will help teach you some tools to make more informed decisions about whether or not things are justified, or at least help you understand what the other side of the argument is and how we can come up with very different numbers, right? Because again, 99.9% accurate sounds really good. Less than 3% accurate does not sound as good. And again, that's the dangerous part about statistics, is that people use the statistic that is going to benefit their argument and probably not tell you the other side. It actually goes back to a very famous quote attributed to Mark Twain, that there are lies, like little white lies, that we tell every day. There are damn lies, which are the big lies that we sometimes hear people spouting all the time. And then there's statistics, which statistics is not going to lie, but it's going to be, well, probably, let's say, massaged in a way that only supports the argument that that person is trying to make. And trying to understand both sides of the argument and understand the mathematics behind it is really, really important, because, well, we have these numbers thrown at us all the time, and hopefully we have a better chance to, well, understand them and deal with them. But speaking of numbers, the last thing we're going to talk about in Chapter 5 is these counting techniques. Because typically when we're doing probabilities, the very difficult part is actually figuring out how big my sample space is, or how big my event space is. You know, these things are not always as straightforward as the examples we've been doing so far. Now, in these more complicated scenarios, we need to use counting techniques, which is sometimes called combinatorics. And combinatorics is really the art of counting. And what we're doing is really trying to answer the question, how many ways can I do blank? So for example, in my closet, I have 8 dress shirts, 5 ties that match all 8 of those dress shirts, and 3 pairs of slacks. So how many different outfits can I make? Well, when we have something like this, and again, we're trying to find out the number of ways we can do things. Typically, the number of ways we can do things, we have to go through each choice one at a time, figure out how many choices there are for each one of these individual events, and then we just multiply them. So I have 8 shirts, so there's 8 ways I can choose my shirts. I have 5 ties, so there's 5 ways I can choose my ties. I have 3 pairs of slacks, so 3 different ways I can choose my slacks. I just multiply those numbers all together. 8 times 5 times 3, I get 120, which means I can make 120 different outfits. And so, again, multiplication is really the key here with most of our counting techniques. Next example, how many different ways can I arrange the 52 cards in a deck of cards? Well, the number of ways, well, now again, there's 52 cards. So how many ways can I choose the first card, times how many ways can I choose the second card, times the third card, and all the way down till I get to the end of my deck, and I'm choosing that 51st card and that 52nd card. Well, the number of ways I can choose the first card is, well, 52. There's 52 cards in the deck, so there's 52 ways I can choose the first card. Now what about the second card? Well, this goes back to that problem with the kings a second ago. Now there's only 51 cards left in the deck, so I only have 51 choices of what I want to put as my second card. Then my third card. Well, now my deck only has 50 cards left in it, and so I can only do that 50 ways. And then 49, and then 48, and then 47, and all the way down till we have the last 2 cards, and there's 2 choices for the second to last card, and then only 1 choice for the last card. This is actually a mathematical phenomenon that occurs quite frequently, where we multiply times every number smaller than, well, what we were given, and we use what are called factorials. And factorials, our notation is actually an exclamation point. And so the number of ways to do this would be what's called 52 factorial. 52 factorial is also an insanely huge number. It is bigger than you can possibly comprehend, and I'm actually including a second link in your email about, well, someone actually did a video talking about how big 52 factorial actually is, and I highly recommend that you watch it because it is bigger than you can possibly fathom. And it actually turns out that when you shuffle a deck of cards, if you get a deck of cards and you shuffle it a couple times, and the cards end up randomly ordered, probabilistically speaking, the order in which your cards have ended up, right? You shuffled your deck of cards. The order in which the cards are, that order has likely never been seen before in the entire history of humanity. No one has ever shuffled a deck of cards and ended up with the same exact combination that you ended up with when you shuffled those 52 cards. And I think that is just a bit mind-blowing. And again, I highly recommend you watch that other video to actually hopefully get a grasp on how big that number really is. But again, that factorial notation, like I said, we use that quite a bit. And as we go through my stat lab and the textbook go through, there's formulas using factorials for doing different things like combinations and permutations. We're going to use we're going to use technology. We're going to use our calculators. But again, that factorial notation really means, so for example, 3 factorial would be 3 times 2 times 1. Every positive whole number smaller than it gets multiplied together. 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1. And you see that these factorials get really big really fast. If I start with 3, I end up at 6. All right, not too bad. If I start with 7, I'm already up past 5,000. And it really only gets bigger from there. Now again, the nice part is when we're doing factorials, you could do this on your calculator. If you hit the math button from the home screen, right, the big one that says math, if you scroll over to where it says PRB, which stands for probability, you will see that there is that exclamation or that factorial notation on the list. Also on that list are the other combinatorics tools we're going to use, which are permutations, which is NPR, combinations, which is NCR, and we use the variables N and R when we talk about combinations and permutations in all of our counting techniques. N is always the total number of objects, and then R is going to be the number we choose from. Now, before we can get to what are combinations and permutations, we want to take just a quick step back, and whenever we're doing problems, we want to ask 2 questions first when we're trying to figure out that answer to, well, how many ways can I do things? The first question is whether the order of your items matter. So if you're trying to talk about a combination lock, well, obviously the order matters, right? The combination lock is not going to unlock if you put the orders in the wrong number, or put the numbers in the wrong order. However, if you were dealt a poker hand, well, you can rearrange the cards in your hand and that doesn't matter. It's the same poker hand, no matter which way you have the cards arranged, so the order would not matter. The second question is whether the items can be replaced and chosen again. So, for example, the way the horses finish a race, well, you can't be replaced and chosen again. If a horse finishes first, it can't also finish 5th. It can only finish in one spot and you can't reuse it, right? However, the symbols in your password, well, sure you can reuse it, right? When you're typing your password, you can use the letter A as many times as you'd like and it's still going to be a valid password. And when we ask these 2 questions, after we get the answers to these 2 questions, we should refer to our table here, where, again, does the order matter and can items be replaced? If the answers to both of those questions are yes, that's our fundamental counting principle, or FCP. And basically that means you're just going to use multiplication or exponents or factorials here. And again, right, multiplication includes those exponents and those factorials. However, if the order matters, but the items cannot be replaced, this is a permutation. So again, if the order in which the items occur matters, but they cannot be replaced, that's a permutation. And if the order does not matter, right, they can be in any order whatsoever, and the items cannot be replaced, that is a combination. Now you'll see this last square in my table. If the items can be replaced, but the order doesn't matter, it's called a combination with replacement. It's actually very simple to actually figure this out, but for some reason it's not really covered in this course. It just involves doing a tiny bit of arithmetic for the number of things you choose. But this would be something where, let's say, the best example I can think of is if you get the family meal at KFC, you get your bucket of chicken, and you can choose 3 sides. Well, it doesn't matter which order you choose your sides in, but they can also be replaced. If you want, you could choose 3 orders of the mashed potatoes or 3 orders of the mac and cheese instead of choosing different ones. But again, we're not really going to cover that in this course, so you're not going to have to worry about that too much. Everything's going to typically fall under the fundamental counting principle, or a permutation, or a combination. So for the next example, how many different combos can be used in a combination lock with 36 digits that are not replaced? All right, because again, your combination lock is not going to have the combination 222. It's going to use 3 different numbers. So we ask our questions. Does the order matter? Of course it does, right? Of course, with a combination lock, you have to put them in the right order. What about replacement? No, we just said they can't be replaced. And if we look at our table, order matters yes, replacement no. That is a permutation. And then my variables, right? N is 36 because we have 36 digits to choose from, but R is 3 because how many am I actually choosing? Well, there's 3 digits in the combination lock. And now again, we're just going to use technology. So the way you use the functions on your calculator, you type N first, so 36. Then you would type math and go over to find the NPR for permutations. Then the number 3 for R, hit enter, and then again your calculator will spit out the answer. So those 42,840 different combos for your combination lock. Although, honestly, maybe it should be called a permutation lock instead, eh? Next example, 27 employees apply to go on a business trip. The company chooses 6 of those employees to go. How many different possible groups might be formed, right? So you have 27 people who want to go. They're only going to choose 6. How many different ways can they choose 6 people out of the 27? Again, ask those 2 important questions first. Does the order matter? Well, no, right? It doesn't matter if you're the first one chosen or the last one chosen. You're still going on the trip. Order doesn't matter. And replacement is also a no, because they can't choose the same person to go twice, otherwise that's not 6 different people. So again, refer back to the table. Order matters no, replacement no. This is a combination. We're choosing 27 people, and out of those 27 people, we're choosing 6. So N is 27, R is 6. So we start off, we type the number 27, then we go to math, find the NCR, all right, and then type 6 because we're choosing 6 of those people, and we get 296,010 different possible groups. So just shy of 300,000 different ways they can choose those 6 people. Now, however, what if out of those 27 employees that applied to go, 16 were women and 11 were men, and the company wants to send 3 women and 3 men, so an equal number of men and women on the trip? How many possible groups might they come up with now? Well, now because we're separated it, we have to actually figure out how many ways there are to choose the women, how many ways there are to choose the men, and we're going to multiply those 2 events together. Yeah, because, well, that's how we do it, right? So the number of groups, well, it means we're going to have to find the combination for the women. So there's 16 women. It's a combination still. We're choosing 3. For the men, there's 11 men to choose from. It's a combination. We choose 3. Again, we use our calculators to figure out each of those individually and multiply them together. And we find out that there's 92,400 possible groups now. And again, hopefully that makes sense too intuitively. With example 10, there's almost 300,000 ways to do it. With example 11, we've now restricted ourselves, right? We've actually put conditions on what we can do. And anytime we restrict ourselves or put conditions, we're going to limit ourselves. And my answer should be smaller. All right, and the last example. How many ways can you rearrange the following letters? A, B, 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 E, F, G, G, H. Well, there's 9 total letters, but some of these are repeated. If there were no repeated letters, then the number of ways would just be, well, 9 factorial, right? There's 9 letters, which means there's 9 choices for the first one, 8 choices for the second one, 7 choices for the third one, 6, and then 5, 4, 3, 2, 1, all the way down. Now, however, the letters B and the letters G are repeated, and there are different ways we could choose those too. Which means the letter B, there's 3 letter B's, which means the way we could, well, arrange those would be 3 factorial. The letter G shows up twice, so there's 2 factorial ways to arrange those. And then we set this up as a fraction. Again, we could have gotten 9 factorial, so that's the top of my fraction. But then we need to divide by those two that are repeated. So 3 factorial and 2 factorial. Again, just be really, really careful when you type these things into your calculator. The order of operations matters. You need to multiply those things on the denominator first before you divide. But if you do all that correctly, you should get the answer 30,240. All right. So that basically wraps up our dependent probabilities and our counting techniques. I have included links to other additional videos for a little bit of extra help in the email I sent out. Take your time. Again, and as always, please let me know if you have any questions. Good luck.